The kinetic energy of a particle of mass m and moving with a constant speed v along a straight line is given by kinetic energy corresponds to its linear motion. KL is equal to half mv square. Equation 1. If the particle is rotating about an axis with an angular speed omega and at a perpendicular distance r, then its linear speed v is equal to omega r. The kinetic energy of the rotating particle is Kr is equal to half mv square, which is equal to half m into omega r whole square, which is also equal to half mr square omega square. Let this be equation 2. Now, consider a rigid body of mass m rotating about an axis with a constant angular speed omega. We can treat the rigid body as a system of n particles of masses m1, m2 and so on mn, which are located at perpendicular distances r1, r2 and so on rn from the axis of rotation respectively. Since the rigid body is rotating at an angular speed omega, the angular speed of all the constituent particles are also equal to omega. The linear speed of each particle can be found using the relation v is equal to omega r. For the ith particle, the linear speed vi is equal to omega ri. Then, kinetic energy of the ith particle is Ki is equal to half mivi square, which is also equal to half miri square omega square. The rotational kinetic energy of a rigid body is the sum of kinetic energies of the constituent particles. K is equal to sigma Ki, which is equal to sigma half miri square omega square, which is also equal to half into sigma miri square into omega square. If we define a new physical quantity, I, that is equal to sigma miri square, then the rotational kinetic energy of a rigid body, K, is equal to half I omega square. Let this be equation 3. Let us compare the two equations 1 and 3, which gives the expression for linear and rotational kinetic energy of a body. The angular speed omega of equation 3 is the rotational analog of the linear speed v of equation 1. Then I must be the rotational analog of mass m in linear motion. I is called the moment of inertia of a rigid body. We know that the mass of a body is the measure of its inertia. Let's see what happens when 3 different masses are placed in front of a compressed spring. We observe that the force exerted by the compressed spring acting on the bodies of different masses is the same for all of them. But when the spring expands, the 3 different masses move through different distances. That is, the greater the mass of a body, the less is the change in its state of linear motion. Or, in other words, the greater the mass of a body, the more is its resistance to any change in its linear motion. Similarly, we can understand moment of inertia as the measure of resistance offered by a body to any change in its rotational motion. That is why moment of inertia is also known as rotational inertia. Let's observe a rotating platform. We see that when a small weight is placed at one end of the platform, its angular speed of rotation decreases. If one more identical weight is placed on it, the angular speed decreases further. This implies that the moment of inertia of a rigid body depends on the mass of the body. If one of the weights is shifted as shown, then we observe that its angular speed of rotation increases. This means that the moment of inertia of a rigid body also depends on the distribution of mass about the axis of rotation. Now, if AB is the axis of rotation, and if the platform is tilted slightly as shown, it rotates about a different axis of rotation, AC. But the angular speed of rotation about AB changes, implying that the moment of inertia depends on the position and orientation of the axis of rotation. The SI unit of moment of inertia is kilogram-meter square, and its dimensional formula is m raised to power 1 and L raised to power 2. Consider a system of 3-point masses, each of mass 0.1 kg, 0.2 kg and 0.3 kg located at 1, 2, 2, 3 and 3, 1 respectively. The moment of inertia of this system of 3 particles about the x-axis, Ix, is equal to sigma m(I)y(I) square, which is equal to m1y1 square plus m2y2 square plus m3y3 square, equal to 0.1 into 2 square plus 0.2 into 3 square plus 0.3 into 1 square, equal to 0.4 plus 1.8 plus 0.3, which is equal to 2.5 kilogram-meter square. Similarly, the moment of inertia of this system of 3 particles about the y-axis, Iy, is equal to sigma mixi square, which is equal to m1 x1 square plus m2 x2 square plus m3 x3 square, equal to 0.1 into 1 square plus 0.2 into 2 square plus 0.3 into 3 square, equal to 0.1 plus 0.8 plus 2.7, which is equal to 3.6 kilogram-meter square. Note, the moment of inertia of a rigid body cannot be calculated by assuming that the whole mass of the body is concentrated at its center of mass. For example, the center of mass of the system of particles discussed earlier is x is equal to m1 x1 plus m2 x2 plus m3 x3 by m1 plus m2 plus m3, which is equal to 0.1 into 1 plus 0.2 into 2 plus 0.3 into 3 by 0.1 plus 0.2 plus 0.3 equal to 2.33, and y is equal to m1y1 plus m2y2 plus m3y3 by m1 plus m2 plus m3, which is equal to 0.1 into 2 plus 0.2 into 3 plus 0.3 into 1 by 0.1 plus 0.2 plus 0.3 equal to 1.83. If we assume that the entire mass of the system is concentrated at its center of mass, then Ix is equal to my square, which is equal to 0.6 into 1.83 square, equal to 2 kilogram meter squared. This is different from the actual moment of inertia of 2.5 kilogram meter squared. Hence, we see that the moment of inertia cannot be calculated by considering the center of mass. If the distribution of mass is continuous, then the moment of inertia is expressed as I is equal to integral of r squared dm. This property of moment of inertia has many practical applications. A good example is a flywheel. A flywheel is a mechanical device with a high moment of inertia. Because of its high moment of inertia, it resists any change in its rotational motion. Flywheels are used in automobile engines and steam engines and help to gradually change the angular speed of the wheel. Consider a small rigid body of mass m attached to a light rod of length r and rotating about the y-axis. What is the moment of inertia of the body? The moment of inertia of a system of particles is given by I equals sigma m(I)r(I) squared. Since we have only one body, I equals mr squared. Now, suppose we split the rigid body into two equal parts, each of mass m by 2, and attach them to two light rods, each of length r. These two masses are placed on either side of the y-axis diametrically opposite to each other and made to rotate about it. The moment of inertia of the system of two bodies is I equals m1r1 squared plus m2r2 squared. On simplification, it equal to mr squared. In another case, the original mass is split into 4 equal parts, each of mass m by 4, and attached to 4 light rods, each of length r, and placed along 4 perpendicular directions from the y-axis. If these 4 masses are made to rotate about the y-axis, the moment of inertia of the system of 4 bodies is I equals m1r1 squared plus m2r2 squared plus m3r3 squared plus m4r4 squared. On simplification, it is equal to mr squared. In all the 3 cases, we can see that the moment of inertia of the system of particles is equal to mr squared. Why is the moment of inertia the same in all the 3 cases? As you know, the moment of inertia of a rigid body depends on its mass and the perpendicular distance of the mass from the axis of rotation. In all the cases discussed, the total mass of the system and its perpendicular distance from the axis of rotation was the same. Hence, the moment of inertia of the system was the same in all cases. By extending the same logic, we can conclude that, firstly, the moment of inertia of a thin uniform ring of mass m and radius r about an axis perpendicular to the plane of the ring and passing through its center is mr square. And secondly, the moment of inertia of a hollow cylinder of mass m and radius r about the axis of cylinder is also equal to mr square. Note that the moment of inertia is independent of the length of the cylinder. Now consider a uniform circular disc. This can be viewed as a body formed by joining concentric rings of different radii together. Using the knowledge of integral calculus, we can derive the expression for the moment of inertia of a uniform circular disc of mass m and radius r about an axis perpendicular to the disc and passing through the center. It is given by the expression I is equal to mr square divided by 2. What is the moment of inertia of a solid cylinder of mass m and radius r about the axis of the cylinder? If you compare uniform circular disc and solid cylinder, there is no change in either the mass of the system or the distribution of mass from the axis of rotation. Hence, the moment of inertia in case of a solid cylinder will be I is equal to mr square by 2. A thin rod can be treated as small mass elements placed along the length of the rod. Using the methods of integral calculus, we can derive the expression for the moment of inertia of a thin rod of mass m and length L about an axis perpendicular to the rod and passing through the midpoint. It is given by the expression I is equal to ml square divided by 12. The moment of inertia of a rectangular plate of mass m, length L, breadth b, about a line parallel to its breadth and passing through the center is I is equal to ml square divided by 12. Similarly, if the axis is changed to a line parallel to the length and passing through the center, I is equal to mb square divided by 12. The moment of inertia of a solid sphere of mass m and radius r about an axis passing through its center is I is equal to 2mr square divided by 5. The moment of inertia of a hollow sphere of mass m and radius r about an axis passing through its center is I is equal to 2mr square divided by 3. The perpendicular axis theorem and parallel axis theorem are related to and help in finding the moment of inertia about different axes if we know the moment of inertia about one axis. The perpendicular axis theorem is applicable only to plane bodies like a thin disc, ring, or a plane lamina, etc. The perpendicular axis theorem states that the moment of inertia of a plane lamina about an axis perpendicular to the plane of the lamina is equal to the sum of its moments of inertia about two perpendicular axes lying in the plane of the lamina and intersecting each other at a point where the axis perpendicular to the plane of the lamina passes through. Let's understand this theorem in detail. Consider a plane body lying in the xy plane and rotating about the z-axis. The plane body can be treated as a system of particles. If the ith particle of mass mi is at a perpendicular distance ri from the axis of rotation and it is identified by the coordinates xi, yi, then using Pythagoras theorem ri square is equal to xi square plus yi square. Hence, the moment of inertia of the ith particle about the x-axis, Ixi, is equal to miyi square. About the y-axis, Iyi is equal to mixi square. And about the z-axis, Izi is equal to mixi square. Put the moment of inertia, I, of a body about a given axis is equal to sigma ii, where ii is the moment of inertia of the ith particle about the same axis. Let ix, iy, iz be the moment of inertia of the body about the x, y and z axes respectively. Then Iz is equal to sigma Izi, which is equal to sigma miri square, equal to sigma mi into xi square plus yi square, which is equal to sigma mixi square plus sigma miyi square, equal to sigma Iyi plus sigma Ixi, equal to Iy plus Ix. This is the mathematical expression of the perpendicular axis theorem. Let us see how we can make use of this theorem to find the moment of inertia of a ring about any of its diameters. Consider a ring of mass m and radius r, placed in the xy plane with its center coinciding with the origin. The moment of inertia of the ring about the z-axis, that is, about the axis perpendicular to the plane of the ring and passing through its center, is denoted by Iz is equal to mr square. If Ix is the moment of inertia of the ring about the x-axis, and Iy is the moment of inertia of the ring about the y-axis, then, using the perpendicular axis theorem, we can write Iz is equal to Ix plus Iy. Hence, Ix plus Iy is equal to mr square. Since the ring is symmetric about the x and y axes, Ix must be equal to Iy. Since Ix plus Iy is equal to mr square and Ix is equal to Iy, we can write Ix is equal to Iy is equal to mr square by 2. This means the moment of inertia of the ring about any of its diameters is mr square by 2. The other useful theorem is the parallel axis theorem, and it is applicable to any rigid body. This can be stated as the moment of inertia of a rigid body about any axis is equal to the moment of inertia about a parallel axis passing through its center of mass, plus the product of the mass of the body and the square of the distance between the two parallel axes. Let's take a rigid body and try to understand this theorem. Let m be the mass of the rigid body, CD be an axis passing through the center of mass, and AB be an axis parallel to CD and at a distance d from it. If ICM is the moment of inertia of the body about CD and IAB is its moment of inertia about an axis AB, then, according to the parallel axis theorem, IAB is equal to ICM plus MD square. The parallel axis theorem is very useful as it helps find the moment of inertia of bodies of any shape or size. For example, the moment of inertia of a solid cylinder of mass m and radius r about the axis of cylinder is ICM is equal to mr square by 2. Now, using the parallel axis theorem, we can find the moment of inertia I of the solid cylinder about an axis parallel to the axis of the cylinder and on the surface of the cylinder. The distance between the two parallel axes is r. According to the parallel axis theorem, I is equal to ICM plus mr square, which is equal to mr square by 2 plus mr square equal to 3 by 2 mr square. Let us look at another example relating to a hollow sphere. The moment of inertia of a hollow sphere of mass m and radius r about an axis passing through its center of mass is denoted by ICM is equal to 2 by 3 mr square. If I is the moment of inertia of this hollow sphere about a tangent parallel to the axis passing through the center of mass, then, according to the parallel axis theorem, I is equal to ICM plus mr square, which is equal to 2 by 3 mr square plus mr square, equal to 5 by 3 mr square. If a solid sphere of mass m and radius r is taken, its moment of inertia about an axis passing through its center is expressed as I is equal to 2 by 5 mr square. This can be written as I is equal to m into square root of 2 by 5r whole square. This is in the form of I is equal to mk square, where k is equal to the square root of 2 by 5 into r. K is known as the radius of gyration of the solid sphere about an axis passing through its center. But what is meant by radius of gyration k? The radius of gyration k of a rigid body about an axis of rotation is the distance between the axis of rotation and a point at which the whole mass of the body can be assumed to be concentrated, so that its moment of inertia would be the same as the actual distribution of mass. Mathematically, k is equal to the square root of I by m. K depends on the geometry of the body and the axis of rotation. Let's find the radius of gyration of a thin rod about an axis perpendicular to the rod and passing through its center. The moment of inertia of a thin rod of mass m and length l about an axis perpendicular to the rod and passing through its center is expressed as I is equal to ml square by 12. The radius of gyration of the rod about the same axis is K is equal to the square root of I by m, which is equal to L by the square root of 12. Using the analogy between translational motion and rotational motion, we can better understand the rotational motion of a rigid body. In the kinematics of translational motion, we studied about linear motion, that is, the motion of a body along a straight line path. The rotational analogy to linear motion along a straight line is rotation about a fixed axis. Let us compare these two motions. Corresponding to linear displacement in translational motion, we have angular displacement in rotational motion. Consider a rigid body rotating about a fixed z-axis and let P be a particle in it. When the rigid body is in rotational motion, the particle P moves along a circular path. Since the rotation is about a fixed axis, the circular path of P lies in a plane perpendicular to the axis of rotation. The angular displacement of the particle in the plane of the circle it moves in is equal to the angular displacement of the rigid body. The rate of angular displacement is angular velocity, omega. Omega is equal to d theta by dt. Omega in rotational motion plays the same role as linear velocity, v, in translational motion. Since the axis of rotation is fixed, the direction of angular velocity is always along the axis of rotation, and hence it need not be treated as a vector. The rate of change in angular velocity is defined as angular acceleration alpha. Alpha is equal to d omega by dt, which also acts along the axis of rotation. Angular acceleration is the rotational analogy of linear acceleration of translational motion. In kinematics of translational motion, we studied about the kinematic equations for a body in linear motion with uniform acceleration. For a body moving with uniform acceleration a, the equations are v is equal to v naught plus at, x is equal to x naught plus v naught t plus half at square, and v square is equal to v naught square plus 2a into x minus x naught, where x naught and v naught are the initial displacement and initial velocity respectively. X and v are the final displacement and final velocity after a time interval of t. Now, let us try to get similar relationships in rotational motion. We shall restrict our discussion to a rigid body rotating with constant angular acceleration about a fixed axis. Consider a rigid body rotating about the z-axis with a constant angular acceleration alpha. Let its angular velocity be changed from omega naught to omega in t seconds. We know that the angular acceleration alpha is equal to d omega by dt. Let this be equation 1. On integrating equation 1, we have integral d omega is equal to integral alpha dt. Since alpha is constant, equation 1 leads to omega is equal to alpha t plus c, where c is the constant of integration. Let this be equation 2. But the initial angular velocity of the body is omega naught. That means, at time t is equal to 0, we have omega equal to omega naught. On substituting these values in equation 2, we get c equal to omega naught. Therefore, equation 2 can be written as omega is equal to omega naught plus alpha t. Let this be equation 3. But we know that omega is equal to d theta by dt. On integrating this equation, we get integral omega dt is equal to integral d theta. If the angular displacement of the body is changed from theta naught to theta in t seconds, integral omega dt from 0 to t is equal to integral d theta from theta naught to theta. Substituting the omega value from equation 3, on further simplification, we get omega naught t plus half alpha t square is equal to theta minus theta naught. Keeping theta on the left, we get theta is equal to theta naught plus omega naught t plus half alpha t square. Let this be equation 4. We know that omega is equal to d theta by dt. D theta by dt can also be written as d theta by d omega into d omega by dt. Therefore, omega is equal to d theta by d omega into d omega by dt. Which is equal to alpha into d theta by d omega. Integrating the expression, we get integral omega d omega is equal to integral alpha d theta, which is equal to alpha into integral d theta. While the angular displacement is changed from theta naught to theta, the angular velocity changed from omega naught to omega. If we integrate the above equation under these limits, we get integral of omega d omega from omega naught to omega is equal to alpha into integral of d theta from theta naught to theta, which is omega square by 2 minus omega naught square by 2 equal to alpha into theta minus theta naught. On further simplification, we have omega square is equal to omega naught square plus 2 alpha into theta minus theta naught. Let this be equation 5. Equations 3. omega is equal to omega naught plus alpha t. 4. Theta is equal to theta naught plus omega naught t plus half alpha t square. And 5. Omega square is equal to omega naught square plus 2 alpha into theta minus theta naught are the kinematic equations for rotational motion with uniform angular acceleration. Example: a flywheel starts from rest and accelerates with a constant angular acceleration of 0.6 radian per second square. Find the magnitude of the angular velocity after turning through an angle of 45 degrees and the time required. Given that initial angular velocity omega naught is equal to 0, angular acceleration alpha is equal to 0.6 radian per second square, angular displacement theta minus theta naught is equal to 45 degrees, which is equal to pi by 4 radians. We know that omega square is equal to omega naught square plus 2 alpha into theta minus theta naught, which is equal to 0 plus 2 into 0.6 into pi by 4, equal to 0.94. Thus, omega is equal to 0.97 radian per second. We also know that theta is equal to theta naught plus omega naught t plus half alpha t square, which is equal to theta minus theta naught equal to omega naught t plus half alpha t square. So, pi by 4 is equal to 0 into t plus half into 0.6 t square. Hence, t square is equal to 2.62 and t is equal to 1.62 seconds. Using the analogy of translational motion and rotational motion, we know that the moment of inertia is the rotational analog of mass in translational motion. Similarly, torque in rotational motion plays the same role as that of force in linear motion. We will now try to derive the expressions for a rotational body about a fixed axis, keeping in mind the dynamics of the system. For simplification purposes, we will consider the rigid body to be rotating about a fixed axis. As the axis is fixed, only the components of torque, which are along the axis of rotation, can cause the body to rotate about the axis. For example, if a body is rotating about a fixed z-axis, then only tau z, a component of torque along the axis of rotation, can cause such rotation. We know that torque tau is equal to R cross F. Thus, the torque acting along the axis of rotation must be perpendicular to the plane containing the position vectors and force. Thus, to calculate torque acting on such a rigid body, we will consider only those forces which lie in a plane perpendicular to the axis of rotation, so that the torque produced by them will lie along the axis of rotation. Only the components of position vectors that lie in a plane perpendicular to the axis of rotation need to be considered for the torque along the axis of rotation. Let's now try to find the work done by the torque for a rigid body rotating about a fixed axis, keeping these considerations in mind. Consider a particle in a rigid body located at P, with its position vector represented by R. The rigid body is rotating about the z-axis. Now, construct a plane containing the particle at P and perpendicular to the axis of rotation. Let us call it the x-y' plane. When the rigid body is in rotational motion, the point P moves along a circle with its center at A. Let the radius of the circle be R1. We can see that the position vector OP is equal to the sum of OA and AP. Thus, OP is equal to OA plus AP. In fact, we see that AP is the component of OP in the x-y' plane. F1 is a force in the x-y' plane acting on the particle at P and makes an angle alpha 1 with the radius vector AP. When the rigid body is in rotational motion, the particle P moves in a circular path, and its position changes from P to P' in a small time interval delta t as shown. The angular displacement of the particle is expressed as angle PA' and is equal to d theta. If the linear displacement of the particle is represented by ds, then its magnitude ds is equal to r1 d theta. Let this be equation 1. A tangent drawn to the circle at P represents the direction of ds. Phi 1 is the angle between the tangent at P and the force F1. From the figure, we see that phi 1 plus alpha 1 is equal to 90 degrees. Let's now find the work done. The work done by the force F1 is dW1 is equal to F1 dot ds, which is equal to F1 into ds cos phi 1. Since phi 1 plus alpha 1 is equal to 90 degrees, thus phi 1 is equal to 90 degrees minus alpha 1. Substituting the value of phi 1 from above, we get dW1 is equal to F1 into ds cos 90 degrees minus alpha 1 equal to F1 into ds sin alpha 1. Substituting the value of ds from equation 1, ds is equal to r1 d theta, we get dW1 is equal to F1 into r1 d theta into sin alpha 1, which is equal to F1 r1 sin alpha 1 into d theta. Since F1 r1 sin alpha 1 is equal to R1 cross F1. We have dW1 is equal to R1 cross F1 into d theta. Substituting tau 1 is equal to R1 cross F1. Thus, dW1 is equal to tau 1 d theta. Let this be equation 2. Here, tau 1 is equal to R1 cross F1 is the torque on the particle along the axis of rotation due to the force F1. If there is more than one force acting on the body, and the work done by different forces is represented by dW2, dW3, and so on, then the work done by all the forces acting on the body, dW, is equal to dW1 plus dW2 plus and so on, which is equal to tau 1 d theta plus tau 2 d theta and so on, equal to tau 1 plus tau 2 and so on into d theta. Since all these torques are along the axis of rotation, we get the total torque on the body as tau is equal to tau 1 plus tau 2 and so on. Therefore, the work done by the total torque acting on a body rotating about a fixed axis is dW is equal to tau d theta. Let this be equation 3. Comparing equation 3 with its translational analogy, where the work done by a force is denoted by dW is equal to Fds, we can see that torque is the rotational analogy of force. Now, let's try to find the rate of doing work, also known as power. We can differentiate equation 3 for the work done by the total torque acting on a body rotating about a fixed axis to find instantaneous power. On differentiating equation 3, dW is equal to tau d theta. We get dW by dt is equal to tau into d theta by dt. But since angular velocity omega is equal to d theta by dt, we get dW by dt is equal to tau omega. However, we know that dW by dt, the rate of work done, is known as power. Thus, power P is equal to dW by dt. We get P is equal to tau omega. Let this be equation 4. Equation 4 is the value of P, which is the instantaneous power. When work is done on a rotating body, its energy must increase. However, in the case of a rigid body, the change in its potential energy must be zero, as there is no change in intermolecular distances. Hence, the increase in energy when work is done on a rotating rigid body increases the kinetic energy of the body. Therefore, the rate of work done on a rigid body rotating about a fixed axis must be equal to the rate of increase in its rotational kinetic energy. We know that the rotational kinetic energy of a rigid body is expressed as Kr is equal to half I omega square. Let this be equation 5. On differentiating equation 5 above, we get the rate of work done, or power, equal to the rate of change of kinetic energy. Thus, we get P is equal to dKr by dt. Substituting the value of P from equation 4, P is equal to tau omega, and Kr from equation 5. Kr is equal to half I omega square. We get tau omega is equal to d half I omega square by dt. Equal to I by 2 into 2 omega d omega by dt, which is equal to I omega alpha, where angular acceleration alpha is equal to d omega by dt. Therefore, tau is equal to I alpha. Let this be equation 6. Equation 6, tau is equal to I alpha, is Newton's second law of rotational motion. It states that the angular acceleration of a rotating body is directly proportional to the applied torque and is inversely proportional to the moment of inertia of the body. You have already learnt that the angular momentum of a system of particles is denoted by L is equal to sigma of Ri cross Pi. Consider a rigid body rotating about a fixed z-axis. Let the position vector of ith particle be Ri and its linear momentum be Pi. Then, its angular momentum about the origin is denoted by Li is equal to Ri cross Pi. If Ri is represented by OP, then it can be written as Ri is equal to OP, which is equal to OC plus CP. We know that Li is equal to Ri cross Pi. Since Ri is equal to OP, which is equal to OC plus CP, then substituting the value of Ri from above, we get Li is equal to OC plus CP cross MIVI. Further simplification gives us Li is equal to OC cross MIVI plus CP cross MIVI. Let this be equation 1, where Vi is the linear velocity of the particle. Equation 1 has two terms on the right side. The first term OC cross MIVI is a vector, perpendicular to both OC and VI. This means this term OC cross MIVI represents a component of angular momentum of ith particle, that is, perpendicular to the axis of rotation. That is, Li perpendicular is equal to OC cross MIVI. The second term, CP cross MIVI, represents a vector that is perpendicular to both CP and VI. Hence, this vector is in the direction of the axis of rotation. As the axis of rotation is along the z-axis, we can call the component of angular momentum of ith particle along the axis of rotation Liz. Hence, Liz is equal to Cp cross MIVI. If Cp is equal to Ri perpendicular and the angular velocity of the rigid body is omega, then the magnitude of Liz is equal to Ri perpendicular cross Mi into omega Ri perpendicular, which is equal to MIRI perpendicular square into omega. Now, equation 1. Li is equal to OC cross MIVI plus CP cross MIVI can be written as Li is equal to Li perpendicular plus Liz. Note that for a particle, angular momentum L need not be in the same direction as angular velocity omega. The total angular momentum of the rigid body rotating about a fixed axis L is equal to sigma Li, which is equal to sigma of Li perpendicular plus Liz. Hence, L is equal to sigma Li perpendicular plus sigma Liz. We get L is equal to L perpendicular plus Lz. Let this be equation 2, where the perpendicular component of angular momentum of the body L perpendicular is equal to sigma OC cross MIVI. Let this be equation 3. And the component of angular momentum along the axis of rotation Lz is equal to sigma of MIRI perpendicular square into omega. Lz is equal to sigma MIRI perpendicular square into omega. Since sigma MIRI perpendicular square is equal to the moment of inertia of body I, we get Lz is equal to I omega. Since this is along the z-axis, we can write Lz is equal to I omega k cap. Let this be equation 4. In general, for a rigid body rotating about a fixed axis, its angular momentum L does not lie along the axis of rotation. Let's take the case of a rigid body that is symmetric about its axis of rotation. From equation 3, the component of its angular momentum perpendicular to its axis of rotation L perpendicular is equal to sigma of OC cross MIVI. Since the rigid body is symmetrical about the axis of rotation, corresponding to every particle with a linear velocity vi, we can find another identical particle with a linear velocity minus vi. This makes the summation sigma of OC cross MIVI equal to 0. For such bodies, L perpendicular is equal to 0. Therefore, L is equal to Lz. This means, for a rigid body that is symmetrical about the axis of rotation, the angular momentum is along its axis of rotation. Now, if we differentiate both sides of equation 2, L is equal to L perpendicular plus Lz. With respect to time, we get dl by dt is equal to dl perpendicular by dt plus dlz by dt. Since dl by dt is equal to tau, we can write tau is equal to tau perpendicular plus tau z. But for rotation about a fixed axis, tau is equal to tau z. Hence, for a body rotating about a fixed axis, dlz by dt is equal to tau z, which is equal to tau k cap, and dl perpendicular by dt is equal to 0. This means, for a body rotating about a fixed axis, the component of its angular momentum perpendicular to the axis of rotation is constant. Let us now look at the law of conservation of angular momentum. If the external torque is 0, then tau net is equal to dlz by dt is equal to 0. Since Lz is equal to I omega, we get tau net is equal to di omega by dt is equal to 0. Now since tau net is equal to 0, then dlz by dt and di omega by dt are also equal to 0. Therefore, we get Lz or I omega as constant. This is the law of conservation of angular momentum pertaining to rotation about a fixed axis. The law of conservation of angular momentum pertaining to rotation about a fixed axis states that, in the absence of net external torque, the total angular momentum of the system remains conserved. Let's demonstrate this with an example. Consider a boy standing at the center of a rotating platform, with his arms stretched out and holding two weights in his hands. We can observe an increase in an angular velocity if he brings his hands close to his body. Since there is no external torque on the system, its angular momentum must be constant. That is, I omega is constant. But when he brings his hands close to his body, I decreases and omega increases. Many sportsmen make use of this law to express their art beautifully. For example, an ice skater changes his angular velocity by changing the position of his hands. You have already studied that a rolling body undergoes simultaneous rotational and translational motion. Let us study rolling motion in detail by observing the motion of the wheels of a remote-controlled toy car. Let us place the car on a sheet of ice. Since the car is at rest, the net force acting on it must be zero. When the remote is switched on, the wheels start rotating about an axis passing through the axle, but they don't roll. This means the wheels exhibit pure rotational motion without any translational motion. Since the surface is smooth, there is no friction between the surface of the ice and the wheels. Hence, the velocity of the center of mass of the wheel VCM remains zero, and the wheels rotate about their axis with a constant angular speed, say omega naught. Now let us spray some dust on the surface to make the surface rough, and place the car on the rough surface and then switch on the remote. We observe the wheels of the car start rolling on the rough surface, though initially they still exhibit some backward slipping motion. When the wheels try to slide backward, the static friction exerted by the surface acts on the wheels in the forward direction. This frictional force provides the required external force that makes the wheels exhibit translational motion. As a result, the wheels will exhibit translational acceleration and the velocity of the center of mass of the wheel increases. Hence, we can conclude that friction is required to start rolling. Now consider the torque due to the frictional force about the center of mass. This produces an angular acceleration, alpha, that decreases the angular speed of the wheel. As a result, the backward slipping reduces and eventually the wheels start rolling without any slipping. This is known as pure rolling. When the wheels roll without slipping, at a given instant of time, a point on the wheel, say P0, in contact with the surface is instantaneously at rest with respect to the surface. Since there is no relative motion between the two surfaces at that instant of time, the static friction acting between the two surfaces must be zero. Now, the wheels can exhibit pure rolling even on a smooth surface. When a body, like the wheel we discussed, is in rolling motion, different particles of the body will experience different velocities. Let us study this by considering a disk of radius r rolling on a flat surface without slipping. Consider two particles C and P on the disk. C is the geometric center of the disk and also represents its center of mass. P is any particle on the disk that is at a distance r from C. While the disk is rolling, the velocity of P has two components. One due to its translational motion, the other due to its rotation about the axis passing through C and parallel to the surface. The translational motion of the rolling body is represented by the motion of its center of mass. This means if the velocity of the center of mass is vcm, then the translational velocity of all particles, including particle P, is equal to vcm. If the angular velocity of the disk about its axis is omega, then P will exhibit a linear velocity Vr due to its rotational motion, which is equal to omega r, and is in the direction perpendicular to Cp as shown. The vector sum of these two velocities, vcm and Vr, will give us the velocity v of point P at that instant of time. Now, consider a point P0 on the disk that is in contact with the surface at that instant. Then, the translational velocity of P0, vcm, acts towards the right, and the linear velocity of P0 due to its rotational motion, Vrp0, is perpendicular to Cp0 and acts towards the left, and its magnitude is equal to omega r. When the disk is rolling without slipping, P0 must be at rest. This is possible only when vcm is equal to Vrp0 is equal to omega r. This is the condition for pure rolling. That means that for any rolling body, if vcm is equal to omega r, then it rolls without slipping. On the other hand, if vcm is less than omega r, the rolling object has some backward slipping, and the rolling is called rolling with backward slipping. For any rolling object, if vcm is greater than omega r, the rolling is called rolling with forward slipping. For example, if a disk is rolling on an inclined plane with slipping, it is rolling with forward slipping. Now, consider another point P1 at the top of the disk as shown. The translational velocity of P1 is again equal to vcm and acts to the right. The magnitude of the linear velocity of P1 due to its rotational motion Vrp1 is equal to omega r and is perpendicular to Cp1 and acts to the right. But we know that when the disk is rolling without slipping, vcm is equal to omega r. Therefore, the velocity of P1, Vp1, is equal to vcm plus Vrp1, which is equal to omega r plus omega r, which is equal to 2 omega r. So when an object is rolling without slipping, the velocity of the center of mass c is vcm is equal to omega r. And the instantaneous velocity of a point like P0 that is in contact with the surface is 0. And the instantaneous velocity of a point like P1 that is at the top is equal to 2 omega r. So far, we have presented the rolling motion as a combination of translational and rotational motion. We can also present the rolling motion as pure rotational motion. An axis passing through the instantaneous point of contact P0 and along the angular velocity omega that is perpendicular to the plane of the disk is called the instantaneous axis of rotation. Each particle of the disk can be considered to rotate about this axis at that instant of time with the same angular velocity omega. Now, if a particle P is considered, then at that instant, the linear velocity v of particle P is perpendicular to P0p, and v is equal to omega into P0p. This must be equal to the vector sum of Vcm and Vr. That means the combined effects of translational motion of the center of mass and rotation about an axis passing through the center of mass are equivalent to pure rotation with the same angular velocity about an axis passing through the point of contact. Now let us compare different motions of a disk. When a disk is in pure translational motion, all points P0, C and P1 move with same velocity that is equal to the velocity of the center of mass Vcm. When a disk is in pure rotational motion, the velocity of its center of mass Vcm is equal to 0. The magnitude of the velocities of P0 and P1 are equal to omega r, but they are opposite in direction. When the disk rolls without slipping, then the velocity of P0 is 0. The velocity of the center of mass is omega r, and the velocity of P1 is double the velocity of the center of mass. We understood that rolling without slipping is possible on a smooth horizontal surface. Is rolling without slipping possible on a smooth inclined surface? Let us first consider the forces acting on a disk rolling on a smooth inclined plane. There are two forces acting on the disk. One is the weight of the disk in a vertically downward direction, which always acts through the center of mass. The other one is the normal reaction force, N, exerted by the surface on the disk. As a result, there is a net force mg sin theta acting along the inclined surface. This makes the disk slide. Hence, rolling without slipping is not possible on a smooth inclined surface. If the surface is rough, there must be a static frictional force F acting on the disk as shown. In such cases, rolling without slipping is possible. While solving problems relating to the rolling of an object on an inclined surface, we can use two different methods. In the first method, we analyze the forces and torque acting on the object. Let us consider the x-axis along the inclined surface and y-axis perpendicular to the inclined surface. Since the body does not exhibit any translational motion along the y-axis, that is, in the direction normal to the inclined plane, using Newton's second law of motion, we can write normal reaction force, N is equal to mg cos theta. Let this be equation 1. If the acceleration of the center of mass of the disk along the x-axis, that is, along the inclined surface, is a, then for motion along the inclined, we can write mg sine theta minus f is equal to ma. Let this be equation 2. Now let us consider the rotational motion of the disk about its center of mass. The torques about the center of mass due to the weight and normal force are 0, as the lines of action of these forces pass through the center of mass. Only the torque about the center of mass due to the frictional force can cause rotational motion in the disk. If the angular acceleration of the rolling object about its center of mass is alpha, then, according to Newton's second law for rotational motion, torque due to friction tau f is equal to I alpha, where I is the moment of inertia of the disk about an axis passing through its center of mass and parallel to the inclined surface. But tau f is equal to Rf. Therefore, Rf is equal to I alpha. Let this be equation 3. In any given problem, we can write these equations and solve them for the unknown. The second method involves the law of conservation of energy. Since, for an object in pure rolling motion, the instantaneous point of contact is at rest, the work done by the frictional force on the rolling object is 0. Hence, for an object rolling on an inclined surface without slipping, a loss in its potential energy must be equal to the gain in kinetic energy. But what is the kinetic energy of the rolling object? Let us derive an expression for the kinetic energy of a rolling body. When a system of particles exhibits simultaneous translational and rotational motion, then the kinetic energy of a system of particles, Ke, can be written as the sum of the kinetic energy of the center of mass, Kcm, and the rotational kinetic energy of the system of particles about its center of mass, Kr. Ke is equal to Kcm plus Kr. Now let us use this relation to find an expression for the kinetic energy of a rolling body. Let m be the mass of the disk, and Vcm be the velocity of the center of mass of the disk. Then, the kinetic energy of the center of mass, Kcm, is equal to half m Vcm square. If I is the moment of inertia and omega is the angular velocity of the disk about an axis passing through the center of mass and parallel to the surface, then the rotational kinetic energy, Kr, is equal to half I omega square. Since the kinetic energy of the rolling body, Ke is equal to Kcm plus Kr, we have Ke is equal to half m Vcm square plus half I omega square. In terms of the radius of gyration, K, the moment of inertia I is equal to mk square. Therefore, the above equation can be written as Ke is equal to half m Vcm square plus half I omega square is equal to half m Vcm square plus half mk square into Vcm by r whole square, or Ke is equal to half m Vcm square into 1 plus k square by r square.